Chemical equilibrium, part 4. The properties of the equilibrium constant K plus examples. Before we get started, let's remind ourselves of a few things that we've already talked about. And so first, we're just going to remind ourselves about this generalized reaction. We have reactants A and B, and lowercase a and lowercase b are their coefficients. And then a similar situation exists for products C and D. Their coefficients are represented by lowercase c and lowercase d. Now, we discussed this equation in context of the law of mass action. And so we demonstrated and discussed the relationship between the value of the equilibrium constant K and the concentrations of products and reactants. And also remember that these powers are the coefficients in our generalized reaction. This is the equilibrium constant expression, and it's always products over reactants. So looking at our generalized reaction again, we have the equilibrium constant expression that we had on the previous slide. Now, if we reverse the reaction, so we make products reactants and reactants products, then the equilibrium constant expression is inverted. And so the value for the equilibrium constant is 1 over k, so 1 divided by the equilibrium constant value, or you can do k to the -1 power. They're equivalent. So bottom line is that if we reverse a reaction, the new equilibrium constant for the reversed reaction is the inverse of the original value. So if we reverse a reaction, we have to take the inverse of the equilibrium constant. All right, another property, we can add two equations together to get a new reaction and get a new equilibrium constant for that reaction. So this might remind you a little bit of Hess's law. We have two reactions here that we're going to add together, so reaction 1 and reaction 2, and each of them have their own equilibrium constant. And so when we add them together, C is on both sides of the equation, so we're going to cancel that out. So we're going to end up with an overall reaction that's A plus B plus D, so everything on the reactant side, and that's going to be in equilibrium with product E. If we want to get the new value for the equilibrium constant, then we multiply the equilibrium constants for the two reactions that we added together. So our new equilibrium constant is going to be the product of K1 and K2, and that will be K3. Now, another property is that if we multiply all of the coefficients by a factor in an equation, then the new equilibrium constant is going to be the original value raised to the power equal to that factor. Okay, so for instance, looking at our original reaction, A plus B is in equilibrium with C, and K had a certain value. If we multiply that entire equation by 4, so we multiply all the coefficients by 4, then the new equilibrium constant value is K to the 4th power. So whatever you do to the coefficients, you're going to take the equilibrium constant to that power. And that works the same way regardless of whether it is a whole number like we just saw or a fraction. So for instance, if we divide all of the coefficients by 4, which is the equivalent of multiplying each one by 1/4, then the equilibrium constant for our new reaction is going to be the equilibrium constant K to the 4th power, or the 4th root of that. So you can write it either way. Okay, so let's look at an example. So we have a reaction where we're reacting nitrogen and hydrogen to get ammonia, and the equilibrium constant for that reaction is 0.118. Now, we want to figure out what the value for the equilibrium constant is for this reaction. So look at it. What did we do to that reaction? Compare it to the first one. Okay, so looking at our original reaction, we see that we had nitrogen and hydrogen reacting to form ammonia. And in our new reaction, we have ammonia that is in equilibrium with nitrogen and hydrogen as products. The equilibrium constant value for the reversed reaction is going to be 1 divided by 0.118, or we can take 0.118 to the -1 power, and we're going to get 8.47. So that's the equilibrium constant for the reversed reaction. So now let's look at adding two reactions together. So we have reaction 1 and reaction 2, and each of those have their own equilibrium constant. 5.1 for the first reaction, 0.15 for the second. So adding those two reactions together, we're going to have 2P plus S is in equilibrium with G. And to get the new equilibrium constant for that reaction, we're going to multiply K1 and K2, and K3 ends up as 0.767. So that is the new equilibrium constant for this reaction. So let's go back to this ammonia reaction. And what we are going to do is multiply each of those coefficients by a factor. So take a look at our new reaction. What did we do? Each of those coefficients in our reaction here was multiplied by 1/3. You could also look at it as dividing by 3. Each of the coefficients were multiplied by 1/3, and so our new equilibrium constant value is going to be our original equilibrium constant to the 1/3 power. Okay, and then we're going to end up with 0.490 for a new equilibrium constant value after we multiplied each coefficient by 1/3. Next, we will talk about ice tables and equilibrium calculations, and that will be part 5.